Sissi Miao from Karlsruhe Institute of Technology in Germany. I'm very happy to present our work at OFC. The paper is called Improved Soft-Aided Error-and-erasure Decoding of Product Codes with Dynamic Reliability Scores. This is joint work with Lukas Hub and Laurent Schmalen. Our proposed decoder falls into the category of hybrid decoder of product codes. Conventionally, product codes are decoded either with soft decision decoding SDD or hard decision decoding HDD. For SDD, we know that it has the benefits of very good error correcting performance, but because we pass soft messages and we use soft decision decoder, the complexity is very high. And if we use hard decision decoding, the complexity is low, but there's usually a coding gain loss, roughly around 1 to 2 dB. And what we are trying to do here is we do a hybrid decoding. We introduce a certain amount of soft information to aid the hard decision decoder, so it approaches the decoding performance of a soft decision decoder, but the performance is similarly low as in the hard decision decoder. And our approach is based on error-and-erasure decoding. This is our decoding model. We consider product codes constructed with BCH or even with subcode of BCH codes as component codes, and the binary values are transmitted over binary input AWGN channel. And conventionally, if we do a hard decision decoding at the receive end, we will perform a hard decision for the bits. If they have a positive value, we will say this is a 0, and if it has a negative value, we'll say this is a 1. And we can see that there's a problem that for the bits that with a very small magnitude, it is very easy that the hard decision makes a mistake. So we think if it is very prone to wrongly quantize a bit, then we can just let the decoder not to choose at the beginning, not to choose at all, and we hope that we decode these bits that are marked as erasures during the iterative decoding. And to do so, we would need a error-and-erasure decoder. The decoder we use is a modification of the decoder from Moon's book. What we do is for a received vector that is ternary with 0, 1 and erasures, we first check if the number of erasures is smaller than the design distance. If this is not the case, we start the decoding by first we fill the erased positions with 2 complementary random vectors. Then we will have y1 and y2, both binary vectors. Then we will perform BDD on 2 vectors, y1 and y2, to obtain 2 decoding outputs. Then we will choose from the 2 decoding outputs to determine the output of the error-and-erasure decoder. This decoder has a very nice property that is possible that we decode beyond the minimum distance. That is to say, if we fill the erased positions with random values, it is possible that we guess them all correctly. But also it is the miscorrection rate is also increased because we easily get to another code word that is not the original code word. And we observe that if we can avoid all the miscorrections, then the decoding performance will be greatly improved. So this brings us to the problem of miscorrection detection. So what we do with our miscorrection detection is we use this very simple idea that if a decoding decision is in conflict with a bit that we think is very highly reliable, that is to say, if a decoding decision tells us to flip a bit that we think is probably correct, we will say this is a miscorrection. And the problem then is how do we identify those bits? How do we know that these bits are highly reliable? We found two approaches from literature. The first one is from soft-aided bit marking, the SABM. This algorithm uses the channel output, so we have already marked the bits with small magnitude as erasures, and also we can also mark the bits with very high magnitude as high reliable, because it's very difficult that like a one goes to here, and but we see the problem that it is still possible that we wrongly mark some bits as highly reliable and they will be persistent and impact our decoding performance. Another approach we found is anchor decoding. It doesn't use a soft channel output, so it's a hard decision decoder, but it is based on the observation that if a bit is erroneous, the row and column decoder will probably disagree upon this bit. So it sets all successfully decoded bits that stays constant during the decoding as anchor bits. And the anchor bits is another name for highly reliable bits. And it also is not allowed to be flipped. Because it doesn't use soft channel output, the marking of anchor bits also not so correct, so accurate. So what our approach here is we introduce additional reliability measurement called dynamic reliability score, the DRS. So this DRS is designed so it reflects the overall reliability of a bits from both the channel output, so as in SABM, and and also its decoding behavior during the iterative decoding, like in the AD. Let's see how we can do it. So First of all, we need to initialize the DRS for every bit. So we first sort the received value, the absolute value of the received value, and we assign for the bits with high magnitude a high DRS, and the bits with low magnitude with low DRS, meaning they are less reliable. And the scores are stored in an additional register, and they are in the range of a small integer, so we don't need a very big additional storage. And then we also will mark erasures and perform hard decision for the non-erased bits, so we have a ternary input for our iterative decoder. And we start the iterative decoding. It is similar as the iterative hard decision decoding. The difference is that we first replace the BDD with error and erasure decoder. And then also after every decoding step, we will perform a miscorrection detection. Only if a decoding decision passes the miscorrection check, will it be accepted. And also we will update the dynamic reliability score with hard messages during the iterative decoding. That is, if a bit stays constant all the time, we will increase the reliability score. And if a bit is constantly getting flipped, we will decrease the reliability score. Then for the bits with high reliability score, we will mark them as anchor bits, same in the name as anchor decoding. And if a decoding decision is conflict with those bits, then this will be regarded as a miscorrection. So let's see the performance of this decoder. We have this plot here with 18 different bits, that is 18 different product codes, and the XX is the rate of the product codes, and YX is the gain we get by using our proposed decoder compared to a conventional hard decision decoder. And we can see for all different kind of codes with different rates, we always get a pretty large decoding gain compared to the hard decision decoder. And furthermore, we plot the decoding gain by using an idea error-and-erasure decoder, which has a perfect miscorrection detection. we can see that our decoder behaves quite close to the transparent markers, and this means that our decoder is really nearly miscorrection free. Then we can see some example codes. The first one is the product codes of rate 0.87. Um, this is the hard decision decoders, the IBDD and anchor decoder, and this is the soft decision decoder, and we can see that there is a quite large gap between them, and these are the hybrid decoders. So this is the SABM we introduced before, and then this is our decoder, so all the solid lines are with 10 iterations. We can see that it outperforms the SABM and has 0.76 dB gain compared to the hard decision decoder. And also, if we further allow 20 iterations, it behaves even closer to the soft decision decoder and is even the same as the idea error-and-erasure decoder. Um, then also we can also observe this gain with another code with a smaller rate, so we have roughly 1 dB compared to the hard decision decoder. So this brings us to the end of my presentation. So in this paper, we improved the error-and-erasure decoding of product codes by introducing a quite successful miscorrection detection mechanism. And also, so the performance is really similar as the soft decision decoding, but we still kept the decoding complexity similarly low as in the hard decision decoder. Thanks for your attention. I'm looking forward to hear your questions.